Hi everyone. So magnetic fields are omnipresent. So along with the astrophysical magnetic field, we have an indirect evidences that there is a cosmic magnetic field. So a well-established theory of the origin of such magnetic fields are not yet there. So we explored the possibility of one such theory, in which the primordial magnetic fields might have originated. So we study the primordial magnetogenesis in the framework of loop quantum cosmology. So loop quantum cosmology is an attempt to extend the inflationary scenario to the Planck regime using the concepts of loop quantum gravity. In this theory, the singularity is replaced by bounds. So before the time t equal to 0, we have a contracting phase and the universe bounces into an expanding phase. So the singularity is replaced by bounds, and after the bounds, there is inflation and the theory continues. So in such a regime, in such a framework, the background is governed by the modified Friedmann-Reichsfeld equations, and in this equation, here the rho supremum is the maximum energy density of the universe, which the universe attains at t equal to 0. That means at bounds. So when the energy density attains the maximum energy density, that is t equal to 0, the scale factor attains the lowest value, which is 1. So in such a context, the scale factor evolution is given by this, and after some 10 power 6 seconds, there is inflation. 10 power 6 Planck seconds, there is inflation. So this is the framework which we work on, and in this context, we are studying the generation of primordial magnetic fields. So the theory is that there were some tiny quantum fluctuations in the primordial regime, and these fluctuations grew along with the evolution of the universe and are present as the cosmic magnetic fields in the present. So even though we tell that it is not that easy, because even the fluctuations are formed, these fluctuations will not evolve, they will just remain as tiny fluctuations, because the standard electromagnetic action is conformally invariant. So any fluctuations produced would not grow and will not be relevant to us. So the conformal invariance has to be broken, and we break the conformal invariance by introducing a function which is dependent on the scale factor, and we take the idea of Jerome and Yokoyama, and we introduce a function which is proportional to scale factor, and the coupling function has a form a power p, and using such a function, the conformal invariance is broken, and this is the modified total action. And in for such an action, the equation of motion of magnetic vector potential, electromagnetic vector potential is this. Here you can see if this F is absent, this is just a simple harmonic oscillator, and such a solution is not relevant to us. So with this equation of motion, we have this magnetic potential, electromagnetic vector potential A, and we are interested in studying the energy distribution, and we study the spectral energy distribution using the power spectrum, which is nothing but the distribution of energy density over the logarithmic scales. So we have the electric and magnetic power spectrum given by this equation, and we study this in the LQC context. So again, in the equation of motion, we have this term F double prime by F, which is effective potential. The square root of effective potential is plotted here, and we have chosen two forms of coupling function, which is a power 2 and a power minus 3, and the evolution of and the root of effective potential is plotted here. So the modes which are here in this range, these modes see the bounds and they will be affected by the bounds, but the modes here, their bounds is not seen by them, and they will not have any effect, and they will show this law of behavior itself. So this we can see in the power spectrum. So this is the power spectrum in LQC context, and here you can see the power spectrum is largely dependent on depending on the scales. These are highly scale dependent. So the modes which are here, they are enhanced, their amplitude is enhanced due to bounds, but in the Slaughter regime, the power spectrum is largely scale invariant. Also, they show a dependence to the form of coupling function. So we summarize that in the LQC context, the power spectrum is largely dependent on the scales in the lower k value, but in the larger k value, they are scale independent, and they also have a high dependence on the coupling function. So I thank the organizers for the opportunity. Thank you.
Thank you, Ganga, for finishing in time.